Langchain NVidia trtllms. Description: NVIDIA TensorRT is a high-performance inference optimizer and runtime that can accelerate the execution of deep learning models, including large language models (LLMs). Langchain provides integration with TensorRT, enabling you to leverage its performance benefits for LLM inference. This allows you to run LLMs more efficiently and with lower latency, especially on NVIDIA GPUs. Inputs: model: the pre-trained LLM model, typically in formats like ONNX or TensorRT engine files. Input text: the text prompt or query you want to feed into the LLM. TensorRT configuration settings for TensorRT, including the optimization level, precision FP16, COVALENTF1P32, INT8, and other parameters to fine-tune the inference pipeline. Outputs: generated text: the output generated by the LLM based on the input text. Inference time: the time taken to execute the inference process. Steps: load model: load the pre-trained LLM model into the TensorRT engine. Preprocess input: prepare the input text according to the requirements of the LLM, such as tokenization or embedding. Run inference: execute the inference process using TensorRT, leveraging its optimized execution environment. Post-process output: convert the output generated by the LLM into a human-readable format. Metrics: inference latency: the time taken to process the input text and generate the output. Throughput: the number of inferences that can be performed per second. Memory usage: the amount of memory consumed by the LLM and the TensorRT engine. Visualization plots: inference time distribution: a histogram showing the distribution of inference times for different input lengths or complexities. Throughput vs. batch size: a plot showcasing how the throughput changes with varying batch sizes. Fine-tune parameters: precision: the level of precision used during inference FP16, COVALENTF1P32, INT8. Lower precision can trade off accuracy for speed. Optimization level: the level of optimization performed by TensorRT. Higher levels often lead to better performance. Workspace size: the amount of memory allocated for TensorRT to perform its operations. Uncertainty methods: ensemble methods utilizing multiple models, possibly with different configurations, to obtain a more robust prediction, resulting in a better estimation of uncertainty. Temperature scaling: modifying the output distribution of the LLM by adjusting the temperature parameter, allowing for more nuanced or less certain predictions. Challenges and fixes. Challenge 1: model compatibility: not all LLM models are compatible with TensorRT. Some may require specific formats or preprocessing steps. Sample use case that resulted in challenge 1: attempting to load a model in a format not supported by TensorRT. Fixes to challenge 1: convert the model to a supported format like ONNX or create a custom TensorRT plugin for the model. Challenge 2: memory constraints: large LLMs might require substantial memory, exceeding the available GPU memory. Sample use case that resulted in challenge 2: attempting to load a large LLM on a GPU with limited memory. Fixes to challenge 2: use model quantization techniques to reduce the model's memory footprint. Use a GPU with more memory, or optimize the TensorRT configuration to reduce memory usage. Challenge 3: performance bottlenecks: the inference process might be hampered by bottlenecks in data transfer or other aspects. Sample use case that resulted in challenge 3: slow inference times despite using TensorRT. Fixes to challenge 3 profile the inference process to identify bottlenecks. Optimize data transfer mechanisms. Adjust TensorRT configuration parameters. And ensure efficient memory management. Langchain NVidia trtllms streaming response generator. Description: the streaming response generator is a class designed for generating responses from NVIDIA Triton-based LLM models in a streaming fashion. It enables the retrieval of responses in chunks, making it suitable for handling large outputs efficiently. The class allows for interaction with Triton-based models that provide streaming outputs, offering a mechanism to receive the results incrementally. Inputs. Model: this input represents the Triton-based LLM model that will be used for generating responses. The model should be configured to support streaming outputs for this generator to function correctly. Prompt: this input defines the prompt or input text that will be provided to the LLM model for generating the response. Temperature: the temperature parameter controls the randomness of the generated response. Higher temperatures introduce more diversity, while lower temperatures tend to produce more deterministic outputs. Top: this parameter, known as nucleus sampling, restricts the probability distribution of the next token to a subset of the most probable candidates. A higher value for top allows for a broader range of tokens, while a lower value focuses on more likely tokens. Top K sampling is a method for selecting the next token based on the top K most probable tokens. A higher value for top considers more candidate tokens, while a lower value focuses on the most likely tokens. Outputs. Response: the response generated by the LLM model in response to the provided prompt. The response is received in chunks, which allows for efficient processing of long outputs. Stream: this output provides the raw stream of tokens generated by the model. The stream consists of individual tokens as they are produced during the response generation process. Steps. Initialize the streaming response generator. This step involves creating an instance of a streaming response generator class. This instance is configured with the Triton-based LLM model and any necessary parameters. Send the prompt to the model. The prompt is sent to the Triton-based model for processing. The model is configured to generate responses in a streaming fashion, returning tokens incrementally. Process the streamed tokens as tokens are received from the model. They are processed by the streaming response generator. These tokens are typically assembled into a coherent response by concatenating them. Return the response once the model has generated all the tokens for the response. The streaming response generator returns the complete response. This response can be accessed in chunks as they become available, allowing for efficient handling of large outputs. Metrics. Response latency. This metric measures the time taken to generate the complete response, from the moment the prompt is sent to the model until the final response is received. Token generation rate. This metric tracks the speed at which tokens are generated by the model. It reflects the efficiency of the model in producing the output. Visualization plots. Response token generation over time. This plot visualizes the rate of token generation during a response generation process. It can reveal patterns in the model's performance and help identify potential bottlenecks. Token probability distribution. This plot displays the probability distribution of tokens generated by the model at each time step. It provides insights into the model's decision-making process and the likelihood of generating specific tokens. Fine-tune parameters. Model architecture. The architecture of the Triton-based LLM model can be fine-tuned to optimize its performance and accuracy for specific tasks. This might involve adjusting the number of layers, the size of hidden units, or other architectural parameters. Training data: the quality and quantity of the training data used to fine-tune the model significantly influence its performance. Selecting relevant and high-quality data for fine-tuning is crucial for achieving desired results. Learning rate: the learning rate controls the step size during optimization. Fine-tuning the learning rate can help the model converge faster and avoid getting stuck in local optima. Batch size: the batch size determines the number of samples processed during each training iteration. Optimizing the batch size can improve training efficiency and prevent overfitting. Uncertainty methods. Temperature sampling: temperature sampling introduces randomness in the token selection process, allowing for exploration of alternative responses and providing a measure of uncertainty. Top K sampling: top K sampling focuses on the K most probable tokens, potentially reducing uncertainty by favoring more likely choices. Nucleus sampling: top P nucleus sampling restricts the probability distribution to a subset of K most probable tokens, offering a balance between exploring diverse options and focusing on the most likely candidates. Challenges and fixes. Challenge 1: handling long responses. The streaming response generator is designed to handle long responses efficiently by processing them in chunks. However, very long responses might still pose challenges, potentially leading to memory constraints or delays. Sample use case that resulted in Challenge 1: generating a comprehensive summary of a lengthy document, potentially exceeding the memory capacity of the streaming response mechanism. Fixes to Challenge 1: increase memory allocation. Adjust the memory resources available for the streaming response generator to accommodate larger responses. Implement chunking mechanisms. Implement additional chunking strategies within the response generation process to break down long responses into manageable segments. Optimize token processing. Optimize the token processing steps to minimize memory consumption and improve processing speed. Challenge 2: handling unpredictable response lengths. The streaming response generator relies on the assumption that the model will provide a consistent stream of tokens. However, some models might generate responses with variable lengths or patterns, leading to challenges in handling the stream. Sample use case that resulted in Challenge 2: a model generating responses with abrupt pauses or unexpected delays in token generation, disrupting the streaming process. Fixes to Challenge 2: implement robust error handling. Include mechanisms to handle unexpected pauses or delays in the token stream, ensuring that the generator can gracefully recover and continue processing. Adapt to dynamic response lengths. Implement strategies to dynamically adjust to the changing response lengths, potentially incorporating buffering or adaptive processing techniques. Explore alternative streaming mechanisms. Investigate alternative streaming protocols or methods that might be better suited for models with unpredictable response patterns. Langchain NVidia trtllms Triton Tensor RT error. Description: the Triton Tensor RT error is an error raised by the Langchain NVidia TRT library when it encounters issues with the Triton Inference Server or Tensor RT during the execution of a model. This error usually indicates problems related to model loading, execution, or communication with the Triton server. Inputs: model file. This is the path to the model file that is being loaded into the Triton Inference Server. Triton server address. This is the address of the Triton Inference Server that the model is being deployed to. Input data: the input data that is being sent to the model for inference. Outputs: error message, a detailed message describing the specific reason for the Triton Tensor RT error. Steps: Model loading. The Langchain NVidia TRT library attempts to load the specified model file into the Triton inference server. Model deployment. The loaded model is deployed to the Triton server for execution. Data input. The input data is sent to the Triton server. Inference execution. The Triton server executes the model on the provided input data. Result retrieval. The Langchain NVidia TRT library attempts to retrieve the results from the Triton server. Metrics. Inference latency. Time taken to complete the inference process. Model size. Size of the model file in bytes or MB. Visualization plots. Model architecture. A visualization of the model's layers and connections. Inference pipeline. A representation of the data flow through the inference process. Fine-tune parameters. Model architecture. Modifying the layers and connections of the model. Optimization techniques. Implementing techniques such as quantization, pruning, and tensor fusion. Uncertainty methods. Monte Carlo dropout. Randomly dropping out units during inference to estimate uncertainty. Bayesian neural networks. Using Bayesian methods to estimate model parameters and uncertainty. Challenges and fixes. Challenge 1. Model loading error. Sample use case that resulted in challenge 1. The model file may be corrupted or in an incompatible format. Fixes to challenge 1. Verify the model file's integrity and format. Ensure it is compatible with Triton and TensorRT. Challenge 2. Model deployment error. Sample use case that resulted in challenge 2. The Triton inference server may be unavailable or misconfigured. Fixes to challenge 2. Check the Triton server's status and ensure it is running correctly. Verify the deployment configuration. Challenge 3. Communication error. Sample use case that resulted in challenge 3. There may be a network issue or firewall blocking communication between the Langchain NVidia TRT library and the Triton server. Fixes to challenge 3. Verify network connectivity. Check firewall rules and ensure the necessary ports are open. Challenge 4. Input data error. Sample use case that resulted in challenge 4. The input data may be malformed or incompatible with the model's input requirements. Fixes to challenge 4. Ensure the input data is in the correct format and dimensions. Verify the data type and encoding. Challenge 5. Inference execution error. Sample use case that resulted in challenge 5. There may be issues with the model's execution, such as resource limitations or GPU memory constraints. Fixes to challenge 5. Optimize the model for memory efficiency. Reduce the batch size or adjust resource allocation. Challenge 6. Result retrieval error. Sample use case that resulted in challenge 6. The Triton server may not return the results properly, or the Langchain NVidia TRT library might not be able to retrieve them. Fixes to challenge 6. Verify the Triton server's configuration for result retrieval. Check the Langchain NVidia TRT library's settings. Langchain NVidia trtllms Triton TensorRT LLM. Description: Triton TensorRT LLM is a Langchain integration with NVIDIA Triton Inference Server, designed for deploying and serving large language models (LLMs) using NVIDIA TensorRT. This approach optimizes inference speed and efficiency by leveraging TensorRT's capabilities to accelerate deep learning models on NVIDIA GPUs. Inputs: Input 1 text prompts or queries. Input 2 model configurations, including the TensorRT model, Triton server information, and other relevant parameters. Outputs: Output 1 text responses generated by the LLM. Output 2 inference statistics, such as latency and throughput, to measure performance. Steps: Step 1: Pre-process the input prompt, tokenizing and converting it into a suitable format for the model. Step 2. Send the processed prompt to the Triton inference server, which uses TensorRT to accelerate the model inference. Step 3. Retrieve the generated response from the server and post-process it. If necessary. Metrics. Metric 1. Inference latency, measuring the time taken to process a single prompt. Metric 2. Inference throughput, indicating the number of prompts processed per second. Visualization plots. Visualization plot 1. Latency distribution over time, showcasing potential bottlenecks. Visualization plot 2. Throughput analysis, revealing the server's capacity and efficiency. Fine-tune parameters. Parameter 1. Model architecture and hyperparameters, which can be adjusted to optimize accuracy and performance for specific tasks. Parameter 2. Triton server configuration, including the number of GPUs, batch sizes, and other settings, to maximize throughput and resource utilization. Uncertainty methods. Uncertainty method 1. Bayesian approaches to estimate the confidence of the model's predictions. Uncertainty method 2. Ensemble methods, combining multiple models to improve robustness and uncertainty quantification. Challenges and fixes. Challenge 1. Model size exceeding available GPU memory. Sample use case that resulted in challenge 1 using large language models with hundreds of billions of parameters on GPUs with limited memory. Fixes to challenge 1. Use a smaller model or consider model quantization for compression. Explore techniques like model partitioning or offloading to CPU for handling large models. Challenge 2. Limited throughput for high latency prompts. Sample use case that resulted in challenge 2. Processing complex prompts with intricate logic, requiring extensive inference time. Fixes to challenge 2. Optimize model architecture and hyperparameters for speed. Consider techniques like batching and parallelization to improve throughput. Investigate server-side optimizations, such as GPU memory management and efficient scheduling. Langchain NVidia trtllms Triton TensorRT runtime error. Description. The Triton TensorRT runtime error is an error that occurs when using the Langchain NVidia Triton LLM model and indicates a problem with the underlying NVIDIA Triton inference server. Inputs. Input the input text to the LLM model. The NVIDIA Triton LLM model object, which encapsulates the model's configuration and connection to the Triton server. Error message: a string containing the detailed error message from the Triton server. None in case of a failure. The LLM won't produce any output. Steps. Initialization. The Langchain NVidia Triton LLM model is initialized and configured to connect to the Triton server. Inference. The LLM attempts to send the input text to the Triton server for processing. Error handling. If an error occurs on the Triton server during processing, the Triton TensorRT runtime error is raised. Inference latency. The time taken for the Triton server to process the input text. Server health. The availability and stability of the Triton server. Inference time distribution. A histogram of the inference time across multiple requests. Server load. A graph depicting the utilization of the Triton server's resources. Model configuration. The configuration of the underlying model used in the Triton server. Triton server parameters. The settings for the Triton server, such as the number of GPUs or the request timeout. Ensemble models. Using multiple Triton servers with different models for inference. Calibration. Adjusting the output probabilities to reflect the model's uncertainty. Challenge 1. Triton server down or unreachable. The Triton server is down or not accessible. Attempting to use the LLM after the Triton server has been stopped or the network connection to the server is lost. Ensure the Triton server is running and accessible. Check the network connectivity between the client and the server. Challenge 2. Invalid model configuration. The model configuration in the Triton server is incorrect or incompatible with the LLM, providing incorrect model name or version to the NVIDIA Triton LLM model object. Verify the correctness of the model name, version, and configuration parameters. Challenge 3. Insufficient GPU resources. The Triton server lacks sufficient GPU resources to handle the inference request. Sample use case that resulted in Challenge 3. Attempting to perform inference on a large input with a high-capacity model on a server with limited GPU memory. Fixes to Challenge 3. Ensure the Triton server has enough GPU memory for the model. Use a smaller model or increase the GPU resources available to the server. Challenge 4. Triton server errors. Errors occurring during the Triton server's processing. Sample use case that resulted in Challenge 4. Malformed input data, errors in model code, or issues with the Triton server's internal components. Fixes to Challenge 4. Review the error logs from the Triton server for detailed information. Troubleshoot and fix the root cause of the error. Challenge 5. Resource exhaustion. The Triton server may be overloaded with too many requests, leading to resource exhaustion. Sample use case that resulted in Challenge 5. Simultaneously sending many inference requests to a server. Fixes to Challenge 5. Increase the server's capacity by adding more GPUs, using a more efficient model, or implementing load balancing techniques.